Okay, I'm going to talk about some work which is in progress with Kajal, who was here for I think a month ago. And so what I'm going to talk about is the subject of scattering amplitudes. And now some of you, I mean, anyone who's taken a course on QFT already knows that the scattering amplitudes are some of the most basic questions you can ask about QFT and gravity. And these are directly related to physical observables, which are calculable by experiments. And the typical approach which one has followed is the approach using Feynman diagrams. And they're essentially diagrammatic rules for describing terms in perturbation theory. So Rajesh has already introduced some of this in the previous talk. Now, you evaluate them usually for time-ordered correlation functions. And for convenience, they are usually evaluated in momentum space. And a very simple example of a non-trivial Feynman diagram, which corresponds to a 2-to-2 scattering. By 2-to-2, I just mean you've got 2 incoming particles and 2 outgoing particles is given as this, up to some factors of I epsilon and so on. Now, one thing that you would notice is that this approach usually involves the usage of what are called off-shell particles, that are particles which do not satisfy the equations of motion. And this, a particular diagram by itself is not a physical observable, but it really forms a building block in basically computing one. Okay. Now, the example that I just showed you in the previous slide was that for a simple scalar field theory, more concretely a phi-cube theory. But in general, when you want to describe nature, you have to use more complicated theories. Like one example is the Yang-Mills theory, which is a more complicated example of a gauge theory that Rajesh already introduced. And we will not go into the details of how you'd construct the Feynman rules. So by Feynman rules, I just mean that I'd written how the propagator looks like. I'm not going to go into all the details of how you do that. But studying higher point amplitudes in Yang-Mills theories was something that led to this entire program on scattering amplitudes. So as an example, by this, this is a computation that shows the value of a 2 to 3 point amplitude if you just try to do it in a brute force manner. And all these terms which are barely visible are effectively things which look like momentum contracted with itself or some polarization vector. And it's essentially some large chunk of terms that you end up getting for a 5-point scattering. Okay. It's kind of, it gets worse as you go along. So for example, if you try to do a computation for the 6-point function, you end up getting, I think, 220 Feynman diagrams, which was more than 100 pages of computation. And this is something that was actually done by Park and Taylor in 1985. Now, they actually mentioned this following quote in the 1985 paper, that we hope to obtain simple analytic form for the answer, making our results not only an experimentalist, but also a theorist's delight. And within a year, they actually managed to do that. And they gave a very simple answer for this entire chunk of terms that appear. Okay. I've just used some notations, which are effectively some dot products between a few momenta. And it just reduces to this one nice term. And I've purposefully not canceled the factor of 4. Because you can actually generalize this formula to what's known as the Park-Taylor amplitude, and you can write down quite a general formula for an n-point function this way. Okay. Now, there also exists a similar problem in gravity, where I think the 4-point function has more than 2,000 terms. And even in this old paper by DeWitt, who first did this calculation, it was he kind of mentioned a similar thing while writing the result for the cross-section, that a large amount of cancellations between terms still has to be dug out of this algebra. And this, combined with the fact that the final answers are so ridiculously simple, leads one to believe that there must be an easier way. And this easier way, it took some time to find it, and it was developed in 2003 by people known as BCFW now. And this eventually led to a lot more developments and kickstarted the Amplitudes program. Okay. Now, all the things that I mentioned till now were progress that had taken place in flat space scattering amplitudes. But we know that our universe is not flat. And typically, if you want to study some things which are remotely close to amplitudes in either ADS or DS, you have to work much harder. because the computation of these correlation functions are usually much harder. And this also requires an understanding of the wave function itself. And somehow that also contains the flat space scattering amplitude. Okay, I'm going to say some more details about what these are. So one thing that you would be interested in computing is what's the state in which you would evaluate your correlation functions. And that's effectively described by a path integral of this form, where you specify the value of your field at some time slice, and you just evaluate this perturbatively. You could also do this in ADS, and I'm going to use these two interchangeably. Now, you have a similar perturbative expansion in these coupling constants for the wave functions. And you also generate what are called Witten diagrams. I mean, they're exactly analogous to those of Feynman diagrams, but slightly more complicated. One difference is that these diagrams usually contain two kinds of propagators, which are, the example is a bulk to boundary and a bulk to bulk propagator. But the bulk to boundary propagators are stuff which are basically connected to the boundary, and the bulk to bulk are things which are just connected within the bulk points. So just as an example for a conformally coupled scalar, this is the value of this Witten diagram, where you have to basically integrate over these two bulk points, and you write down your bulk to boundary propagators and your bulk to bulk propagator. Now, this itself has three terms, and you have to perform the integration over these theta functions, which are not hard to do, but the thing is, it soon gets very messy. Like for a for this 4-point function, it's kind of easy to do, and it's not that difficult. But if you ask questions about higher point functions, then you have to perhaps devise new ways in which you can write the answer down. And that is because you actually notice that if you sum those three terms that I wrote down here, sum these three terms coming here, you actually get an answer that's very simple. This x1 and x2 are basically k1s and k2s and so on. And since the final answer is again so simple, you would expect that there is a simpler way to do this calculation than to just brute force write down your Feynman rules and add them. So one such rule was actually discovered by Nima, Benincasa, and Postnikov in 2017, which is it's kind of a clipping rule, where you effectively, if you have a diagram of this kind, which is a shorthand notation for the diagram that I drew previously, it kind of can it can be written down as a product of two lower point amplitudes. Okay, and these are simplifications that don't occur at the level of the full amplitude, unlike the recursion relations developed by BCFW, but they occur at a diagrammatic level. So you have to so these simplify your calculations at a diagram by diagram level, but not at the level of the whole amplitude itself. There does exist a BCFW recursion relation for tree-level correlation functions in Yang-Mills gravity, which was developed by Suvrat. And these simplify your computations by a large amount, along with the complications that I described here. In Yang-Mills gravity, you also have to take care of the fact that these are gauge theories, and you have to contract them with polarization vectors and so on. And you soon end up getting very messy expressions. But the BCFW recursion relation again simplifies them. And they also allow you to get what's known as the flat space limit in momentum space, which ends up giving you the scattering amplitude. Okay, now something that I've been trying to do now is to understand how you would extend some part of this procedure to loop level. Until now, a large part of it has been done for tree level. And one thing that I've been trying to explore now is how do you do it for loop level? Using these clipping rules by Cunningham et al. Can simplify writing the integrands in to a large extent, with a few exceptions. Like for these cactus diagrams, you cannot simplify the integrands using the methods. You have to use the conventional methods. But for something like these kind of diagrams, you can actually write down the integrands in a very nice form, which gives you dealable partial fractions, and you can integrate them. So here I've integrated everything using a hard cutoff, which I've denoted by lambda. And you can do similar computations for 2-to-2 scattering like this. We could also actually write down the answer for a 2-loop amplitudes, which gives an answer of this kind, with these ni's being some order 1 numbers, which are just too messy to write down now. Okay, one thing which we are trying to do now is to understand the triangle diagram. which we can evaluate this in the squeeze limit, where you basically squeeze the to momentum, or you take the collinear limit, and it reduces to some very nice form. Something which we are now trying to understand is how do you renormalize these diagrams, and what implications do they have for the boundary CFT? Can you read off anomalous dimensions from log K terms, and whether you can understand more properties of these diagrams, like properties like unitarity and so on. One question is, can you develop a similar BCFW that Subrat had for, let's say, loop level integrants in angles of gravity, and also whether you can improve the regularization procedure and actually use dim reg instead of hard cutoff. So thank you.
So are there any questions?
Loop diagrams, like one knows how they look like already in flat space, right?
Right.
How much does that constrain the final answer?
So one thing that—
does it help that you know already the answers in flat space?
Right. So one thing that you would expect is to recover the flat space limit of this. Now the issue with flat space limit are these log Ks, because usually the procedure which you use is to compute the residue as the total energies go to zero. But with these log Ks, I'm slightly unsure how to do it. So that's something I'm thinking about, on how do you, whether you can constrain these amplitudes in that way. But I don't have a clear answer yet.
Just one more question and then I'll stop. So the ultraviolet divergences that you get as lambda tends to infinity, those should match the flat space, right?
I think they do. I mean,
and that you have
lambda square.
And that you have checked.
Yeah, I think that the finite terms are things that I have to worry about.
Yeah. The simple Feynman diagram as diagrammatics has a simple generalization from scalar, you have for scalars, fermions, everything. Does your sort of computation also generalize to Gates theories and all,
so
this simplification of diagrams?
Right. So I mean, like I said, one of the central rules that's allowing us to actually do these integrals is to recast them in terms of some nice partial fractions, which kind of follows from this clipping rules developed by Niemann company. And that is something that you can at least, a part of it can be generalized to Yang-Mills. But the issue with Yang-Mills is that along with integrating over such bulk points and having scalar integrals, you've also got some parts which involve taking the dot products of polarization vectors with momentum, terms of this kind. Now, we don't quite know how to deal with them at loop level. At tree level, Subrat's BCFW prescription gives you something, but at loop level, we don't know how to make it work.